This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning, afternoon. Welcome to week 5. We're now a third of the way through semester. Project 1 is in swing. We're all excited about doing a fun project together. Most of you have found teams now for the project, but a few of you are still looking, which is totally fine. If you're looking, of course, you can email me for help. I did have the random pool process though for this reason. It's easier for me to track who's looking and stuff. I'll always help if you email me, but I do encourage you now, if you're still looking for another team member or two, to just post on the LMS discussion board forum for Project 1. As you'll see, there's lots of people doing it. There's no shame in doing that. But you want to start really looking at the data now and really be starting working on the project. And as a reminder, you want to be only submitting to Kaggle as a group. Okay. So, and one little announcement to do with the project, which I'll put on LMS, of course, is I'm going to refine the marking formula for the Kaggle component to make it a little bit more complicated and a little bit more fair. I think that some students might do a bit better than I imagined, and I also don't think it's fair to expect everyone to do that. So I'm going to introduce something that makes it fair for everyone. So stay tuned. I'll do that today so that it's not too far into the project to make that change. I usually don't like to change that kind of thing at all. Okay, so no big changes though. We are finishing off neural networks today. We've been talking about this deck already, and what we're up to is CNNs and autoencoders. And depending how quick we go, we might make a start on SVMs and kernel methods today or not, we'll see. Okay, so we've done all of this and we've talked about how, the current view on deep learning is that you're learning like low-level representations. So you're kind of learning features. And it's really convenient to see this with CNNs and to see it with computer vision applications. So that's what I'll be talking about today. Okay, so we talked about all this already. Okay, right. So I've talked about fully connected feed-forward networks. Fully connected as in each layer, you've got like a fully connected layer. It means that all of the nodes in that layer have incoming edges from every node in the previous layer. Fully connected. Right? And all of the weights on those edges, so we've got number of nodes times number of nodes previous layer times number of nodes next layer, Cartesian product. All of those edges are potentially different weights. So in the standard feed-forward, fully connected layer, each of those weights are potentially different parameters. There's no sharing of parameters. And there could even be extra parameters for like bias terms or intercept terms. Okay. So CNNs make a slightly different, they have two slight differences. One, there's not necessarily full connection or not sort of in the standard sense, but the main difference is the second one, where we have a lot of weight sharing. So a lot of the weights on those edges are now sort of the same weights. So that has implications for how the layer makes predictions, like how outputs are computed, obviously. And it's particularly good for data where there's translation invariance. So it means if I'm trying to recognize in an image a balloon, a red balloon or something, it doesn't matter where in the image it happens, the way I want to recognize it is the same. I don't matter where things are moved to, so I can translate and it doesn't make a difference. That's translation invariance. Speech recognition is another situation where this is important. There's a whole time series of speech, right? I'm thinking about sliding windows. So I'm going to talk about a sliding window here. That happens in speech as well, and also sort of in sequences of text. So these are domains where CNNs seem to work well. People apply CNNs to other domains. Sometimes they work well, but sometimes they don't. So they're not like a magic bullet for everything. They're silver bullet for everything. They're really for sort of translation variant kind of domains. Okay, so what is a convolutional layer? So I'm going to describe it first where our layers are like these nice linear structures. So just an array, a one-dimensional array of input nodes in the previous layer, and then I'm going to have a nice one-dimensional array of nodes in the next layer. But then in the next slides, these things will become 2D arrays and multiple dimensional arrays. So they start off as like vectors, because that's a 1D array. But then when you go to 2D arrays, that's a matrix, okay? And when you go to 3 or more D arrays, that's just called a tensor, okay? But it's no different to a multiple dimensional array. And nothing really changes. Okay, so let's do 1D array. So I've got my input vector of A's. This could be input features. They could be pixel intensities in an image, and I've flattened them into a 1D array, except I won't do that in general. I'll keep it as a matrix. And then I want to compute the output of this convolution. Okay, so what that involves is a weighted sum, just like in the normal fully connected layer. But now to compute one of these sort of next level things, one of the inputs into the next layer, it's not a fully connected operation. So I'm not taking a weighted sum of all of the inputs. I'm just taking a weighted sum of a little window. And that's determined by how many weights I have. Okay, so in this picture I've got 3 weights. So the window is like, you could think of it as width 3. And I do my little weighted sum of W1, 2, 3 with A1, 2, 3, weighted sum, and that goes into this. Now there could be an activation function, etc. Right? So that's one difference. It's not fully connected. Now for the second difference, what if I want to compute the next one? I slide the window along, and I don't change the weights. Okay, so I've shared the weights. So that's the second difference. Okay. And so all I do is I just slide this window along with the same weights, and I just take the same weighted sum, the same dot product as before, right? With the same weights sliding along the previous layer. And so that operation is called a convolution. So it wasn't invented with neural networks. Convolutions are extremely old kind of operation you can take. And part of the reason they're appearing here is that convolutions are really useful in image analysis. So long before people were using neural networks for image analysis, and certainly before neural networks came back in fashion, people were doing convolutions of images with little vectors, and they wouldn't call them weights, because weights is a neural network idea, right? They were calling them kernels or filters. Okay, so you might see that language used, but it just means like a weight vector, right? And one confusing thing, and I'm sorry about this, it's not my fault though, the word kernel, just like bias, it's used in lots of ways in machine learning. There are many ways. Kernel is something that appears in linear algebra. It's an idea in linear algebra that you don't necessarily see a whole lot of machine learning, but you might see it in optimizing things, kernels of transformations. There's also kernel methods, where we have a dot product in a feature space. So we'll get to that maybe later today, maybe Thursday. That's a different kernel to this weight vector. Okay, this is also like a kernel. So, and if I wanted to write this dot product and then slide, dot product and slide as one mathematical operation, where the input is, a vector of the previous layer's things, so that's the A vector, and the input is also the W vector, the set of weights, and the output is now not a single scalar, but the vector of the whole next layer, B vector, bold, then I can write it like this. Okay, so I can write it as this dot product, but now the indexing in the dot product looks a little bit different, that's all. Right? So like for each element, this is sort of saying where am I in the window. And shorthand, we can introduce an operator. So instead of a dot, or instead of angle brackets, or instead of doing a matrix transpose, I can have this asterisk looking operator, unless it means something else. That context tells you it means something else, it often means convolution. Like that's often the way you denote the convolutions with this asterisk. And it's a lot like a dot product, but it's different. And it's important to remember the output isn't a scalar like a dot product. It's a vector. And the dimension of B is going to depend on the dimension of A and the dimension of W. Right? So if you sort of think about how many times can I put W into A and slide it along one at a time, that's telling you the dimension of B. So it's something like the length of A minus the length of W, but I might be off by 1, right? Something like that. But you could always define it to be different. You could not slide it one at a time. You could just sort of jump. You could do skips. You could do other things, right? But often it's one at a time. And that's what a convolution really means. So that's a convolution in sort of slow motion with 1D. Okay, we're just sliding this thing along, and we're getting a vector out. Now, there's nothing special about 1D. It's just a 1D array. But if I've really got data that is structured like a matrix, right, like an image, it might not make sense to flatten it as a 1D thing. Because I'm storing it as a 2D thing, why not keep it that way? It's maybe more efficient. Maybe I'm using a GPU that is very good at working with matrices. So like why mess with something that's working well, right? GPUs is hardware designed for one thing, for doing graphics, which involves transforming stuff in a whole lot of linear algebra. So if I had 2D data, or a 2D output of a layer, right, I could do the same thing. Now my weight vector becomes a weight matrix. And I still slide it along, but I don't just slide it in one direction. I have to kind of slide it in both directions, yeah? So first I might slide it along the row. So just like top row, moving it along column by column, and then I'll go to the next one and I'll keep going. So I just kind of slide this thing along, taking this kind of dot product, or a matrix product, right? And I just do this and I get a matrix as the output. And its dimensions will be determined by the dimensions of the previous layer and the dimensions of the filter, or the weight matrix. But it's exactly the same thing, and this is also a convolution. Okay? And I'm using the word pixel because, you would see this with images. And this is sliding along like this. And here it is in maths. It's a nested for loop. Right? Because when I'm calculating one of these output pixel values or feature values, I've got to do, I've overlaid my weight matrix onto the image somewhere, and I've got to do a sum across the rows and columns of these two things. So that's why I've got a double sum. It's exactly the same thing. And in fact, if you wanted to, you could flatten the input layer and flatten the weight matrix, flatten these two matrices and make them into 1D arrays again, and the convolution would work. It would actually be the same convolution, more or less. There's a little bit of like, would the W matrix hang over the edge or not? It wouldn't quite be the same. It'll be very similar. There'd be a bit more jumping going on. Okay, so that's a convolution. and you can sort of see why we're getting matrices as hidden layers, right? Because if we were only doing, fully connected or something, and we weren't doing this convolutional thing, that we'd be doing dot products, and there wouldn't really be much need per se in having a matrix sort of shaped hidden layer. But because we're doing convolutional layers, we should expect to see things of that dimension, things of that shape, popping up as outputs of our layers. So we can do this even more, because if we've got an image, the image actually might be given to us not as single pixel values, but as channels. So you might have a red channel, a green channel, a blue channel, etc. There might even be transparency or something as well. So an image might not just be one matrix, it might be several matrices overlaid on top of each other. So that's not a 2D array, that's a 3D array. Now the input layer might be a 3D array, and I want to do a convolution on it. I could do 2D convolutions on it, I could do 3D convolutions, so the weight object might now be a 3-dimensional array, and I might be sweeping it through the multi-channel image, and the output of that operation would be another multi-dimensional thing. And in maths, we just call those things tensors. But if you see tensor, don't be impressed. It just means multi-dimensional array. It's not so exciting. Okay. Sounds cool though. And in fact, just like GPUs are designed to be fast at doing two-dimensional and one-dimensional array operations, matrix operations and vectors, you can say, could I have hardware that could do multi-dimensional array operations quickly? And yes, that's tensor processing units, or TPUs. And that's all they are. It's not so exciting, right? But if you can structure your computation to have a lot of these operations, and then have special purpose hardware that does this really fast, maybe that's a good idea. Okay. And again, same notation. Okay. So one thing we could do is take these filters or kernels or weight matrices and visualize them. Now, in this slide, I'm imagining we might have even hand-selected this weight matrix. We might have drawn it by hand. But of course, in neural networks, the whole point is we don't want to design the neural network by hand. We use backprop from Thursday last week to learn the W's. And I'm not going to talk specifically about how the W's are learnt in a CNN because it's exactly the same thing. It's just backprop. All we've got to do is compute these things, and at the end we're going to have outputs of our big network. We're going to have a loss function, we're going to have training data, and we're going to hit the network and the weights with stochastic gradient descent with training data. And so for some training examples where the network is getting high error or high loss, we're going to calculate gradients of all of our weights all through the network, and we're going to follow the negative gradient direction, okay, to improve the weights. And over time, we're going to learn better weights, right? So these aren't hand-drawn or hand-designed. You can, but if you have a really big network, it's impossible, right? So I'm not saying where this weight matrix came from. Maybe you drew it, maybe it was learnt. Okay. But if you had a weight matrix, a low-level one at sort of your first hidden layer, you could potentially say, well, in computer vision, it might make sense to actually visualize the weights themselves to see what's going on. And it can also help you understand why we would do a convolution in the first place, which is kind of like asking, why would I do a weighted sum or a dot product? So suppose this was an input image. It's like part of a character drawn or a pen stroke or something. It's obviously contrived, I've made this up. And so that might be the input image. And then we might just have a simple 3x3 filter, 3x3 weight matrix. Okay. And we could ask, what does the output look like? What does it mean to do a convolution between these two things? Well, what it means is we're kind of asking if the filter is kind of recognizing something, if you think of the filter as like a pattern that we're trying to match, for example, a vertical edge in the input image That would make sense to build features that recognize vertical edges, horizontal edges, curves, textures of tree trunks, textures of leaves, textures of grass and clouds and stuff like that. If you had weight matrices that could recognize all of these things, if there was a way to like apply those weight matrices to an image to figure out where those features are present, then that would be a cool thing to do, because then you'd have like a feature representation, not just raw images. Well, that's exactly what the dot product or the convolution does. The convolution just sweeps it across, searching for where that feature is active. But a dot product wouldn't do that. It would just say, is the whole thing matching? So this little filter is designed to match a little vertical stroke, a sort of a local part of the image that looks like a vertical line. And so when the image looks like that, so you sort of have like some colours on each side, but then sort of one colour in the middle, kind of like a vertical line, and I could have mistakes here, this is all kind of hand done, it will activate like this. And it's a little bit hard to kind of visualise what's going on, but what it's doing is essentially saying high values might be sort of activation, so up here, sort of yellow, and so I'm sort of finding a line up here. So around here, I'm like in the middle of a vertical line or something like that. There's some vertical lines over here. Over here, there's not much vertical line. Over here, it's like, yeah, not much. So this is kind of like anti-correlated with a vertical line, which might be also vertical. Over here, not so much. You know, maybe this is an edge and maybe this is an edge, I don't know. But we need more features. We need to like apply some other things as well. So the view that neural networks is learning low-level features and the middle-level features and its learning representations is the view that you're coming up with these weights somehow. And when people train these really big deep learning models on images and then visualize the weights and visualize like the activation of hidden layers, they see pictures like this and it makes them feel confident that the deep learner is learning something semantically meaningful. So that's kind of, you know, a bit more intuition as to what a convolution is doing, and you know what the weights kind of correspond to and what activation of hidden layers kind of means. And you could do this with like a horizontal one as well, and you could do this with a whole lot of things. But you can imagine once you had activation of a whole lot of these features, you could now build another layer on top that says, oh, when I have like this horizontal thing here and this vertical thing here, I've got a vertex or a corner. And then I build these things up and I might have characters. Yes, question? Excellent question. So the question was, how does this deal with scale? So one thing that has existed for a long time, in computer vision and image processing, they've had this thing called like the Gaussian pyramid or the Blow pyramid. They had some name to do with pyramid and you know whatever. So basically the idea is you can successively shrink your image. So you start with your image normal size, and then you shrink it. And the way you shrink it might not be just throwing pixels out. It might be taking averages of them. So you do like a 3x3 little window, and you take the average, and that becomes 1 pixel. You do a 3x3, that becomes another pixel. And that is like a blur, or it's like convolving with a Gaussian or something. And you get smaller and smaller images, and you could reapply the filter on each of these scales, and you could look for like the maximum activation or something. So that could be a way of having scale invariance for matching things. Now, one of the layers I'm going to talk about later is a max pooling thing, which could be seen as similar to that. But the idea is you could build layers that do this. And then all you need to do in order to use the machinery of backprop to make sure you can tune the layers that do have weights, as long as you can kind of pass back gradients, then you're fine. So if you introduce some weird kind of like smoothing thing or maxing thing or something, as long as you can reason about what the gradient is, the derivatives, it doesn't matter. So the beauty of these kind of compositions of layers is you can still use gradient descent on them as long as you can do derivatives. And the tools now that come with these neural network frameworks like TensorFlow, etc., is that they have autodiff. So as long as you write your layers in the language that the tool is for, say Python or something, there's a library autodiff that will kind of differentiate your code actually take derivatives of code. So you can do all of these things and it doesn't break the neural network. So yeah, good question. Okay, so suppose we had at the lower level, a desire to have a bunch of these like low-level features, if you like. We can do that. So instead of making the first layer, the first hidden layer, it sort of be outputting a matrix which corresponds to one feature, one weight matrix. What if we just stack our filters of interest? Vertical line, horizontal line, diagonal line, leaves, trunk, whatever. What if we stacked them and made a multi-dimensional array, like a 3D array? So here I've just taken 2 filters, but I've got ... so I might have more. I could just stack them. And so now I'm convolving a 2D image, which is the thing on the left, with a 3D array, which is a tensor, which is all of my weight matrices and filters kind of stacked together. I've just stacked them together, I'm convolving them together, and I'm going to get the output of that layer to be the same kind of shape as those filters, or those weights. So I don't have to do this one layer at a time, I could do it all in one layer. And you could think about it as doing really low-level features first. And then if I build another layer on top of this, so doing stuff, downsampling, which I'll explain, further convolutions, which I've sort of said, I can now build higher-level features on top of these lower-level features. And so that's kind of the picture you have in your mind about how these networks are making predictions. How they learn, again, is no different to Thursday. Okay. Yeah, question.
So if you have a multi-dimensional filter,
yeah.
Is there anything that makes it sort of keep the layers of the filter separate, or can they have sort of some parts of the filter that use 2 layers at once to do something sort of more complicated with the inputs?
So the question is, and I'm repeating it for people at home, can you, how much control, and I'm paraphrasing a bit, how much control do you have over what the filters are using and how they're used and how much they're shared and all of that kind of stuff? I mean, I might have missed some of the nuance of what you're asking. I'll show, I think, a green slide later on that has a crazy kind of architecture. It's from NLP, where you have some sharing of things and then some where it's completely separates and then comes back again later. And pretty much if you can imagine by hand some things being shared and some things being not and some things being acted on multiple times and everything else, and if you could write that as code, you could probably use it in a neural network. And you could even have layers that are other learning algorithms, or other models. As long as kind of it makes sense that gradients are going to be going through these things, then it makes sense, yeah. But you could also do something that doesn't make sense in a gradient sense, and just when it comes time to gradient descent, not update that layer. So when you're updating layers in a neural network, there's nothing saying you have to update all of the weights in the network. You could say, I've trained a bunch of layers on another problem in computer vision. I've pre-trained the network. Or I might be doing NLP and having text, and I might have a large corpus of text, and I might pre-train a model to be a language model or something, so outputs likelihoods of words given sort of their occurrence. I could keep those layers for a future network and just put more layers on top. And they're just lower level features. It's just like basis expansion. And you don't have to keep training those layers if you don't want to, or you can. So sort of there's a lot of flexibility in neural networks, which is one. From an engineering viewpoint, people like them a lot. Okay, so here's an example, sort of putting some of this stuff together. So suppose I wanted to identify the number of cells in a scan of a biological sample. So I've taken a microscope image of a biological sample and I'm counting cells. So it looks like there are 3 cells here, right? So how could you do this? Well, you could throw it into a big neural network, but maybe a CNN. So we could have a whole lot of 2D convolutions for our first layer, and we could just stack them, and so that's You know, we get a tensor out. So this is like a tensor. Now we could downsample or max pull, which we'll talk about in a bit in more detail. Could do some more convolutions. And some of the convolutions could be across sort of slices of a tensor. Some of them might not be. So here, I might be doing a whole lot of 2D convolutions to get these slices. But to go from this to this, I might actually be sweeping not a 2D matrix across these things one at a time, but I might be sweeping like a 3D array across them, like a tensor. So it really sort of depends. Do you think the next layer needs to make use of a whole lot of features at once from the previous layer? Then you probably want to be sweeping something that's using all of them at once. If you want to just have a separate thing, you don't need to kind of do it all at once. Okay. You just kind of do a whole lot of stuff, right? But the picture you should be forming is you can mix and match layers. You can have some big, some small. And I'll talk about autoencoding at the end of this deck, which talks about having very small layers. Sometimes it's good to have small layers. Okay. Linear regression, because we want to count how many cells there are. I just want to output one number. Okay, so often you see in CNNs convolutional layers, we've talked about that, and max pooling, and fully connected, which we've talked about. So let's talk about max pooling, which is about rescaling to smaller resolutions, and it limits the number of parameters we have in a sense, kind of encourages regularization in a sense. It's a little bit like this question from before, the first question we had about scale invariance, although not necessarily. I mean, you could do it that way. Okay, so how does it work? Well, let's just invent a new layer. Let's just make something up, right? So what we're going to do is we're going to have a little window, a patch, an M by M patch, where we're going to take that window and we're not going to add them up, we're not going to do a weighted sum, we're not going to do anything fancy, no smoothing. We're just going to take the maximum of all of the values in the patch. Just the max. So almost all of the members of the patch could be small values, like not much activation, but maybe one of them activated a lot. That's going to be the value of the max pooling. Okay, so max pooling is just taking a max of a pool. Now we need to think about what the derivatives of this thing would be. So sort of derivatives of the output of this layer. This layer will have a matrix or tensor-shaped output, multi-dimensional array output, given a multi-dimensional array input. So we kind of need derivatives of the output with respect to input, not because there are any parameters to tune in this layer. There's nothing. It's just fixed. But we need to be able to pass back derivatives to previous layers in order to do backpropagation. So we could use autodiff, or we can think about what it does. It turns out that the derivative is fairly simple. So if you look at a patch, well, I think I talk about it in the next slide, but basically if the output of the patch takes on the value of a particular input, one of the inputs, then the derivative with respect to that input will be 1. If the output isn't maximized by one of the inputs, then the derivative is 0. So it's just like a 0 or 1 valued derivative, and it just depends on what value the patch takes. So here it is, yeah. So if you need to think about what the derivative is, it ends up being not a complicated expression. But autodiff could figure this out. Okay. And again, you wouldn't use this within the layer, it's for the layers before it. Okay. So how would this look like in operation? When you're doing forward passes to evaluate the network, you're just taking maxes. Easy. And you want to remember those values. Which input was actually the maximum for the patch? And then when you're going backwards, the derivative will just be 1 for that one and will be 0 everywhere else. It's nice and simple. Okay. And I haven't said why that's the derivative. Okay. So that's another layer. That's sort of another useful layer in convolution. Again, it's just what it's doing is it's sort of saying it reduces parameters because we end up with a smaller dimension layer after doing it, so we don't have as many parameters. So it's a form of regularization, max pooling, and I'll talk about convolution in a sec about this. But also max pooling is giving you kind of robustness. So it's saying somewhere in this patch there was a vertical line. Somewhere the vertical line filter activated bright yellow, right? So I'm going to say after max pooling, yeah, there's a vertical line somewhere, right? I don't care if it's shifted a little bit. I don't care exactly where the vertical line is. I don't really care exactly how you write your number 9. It's got a slightly vertical bit in it. It doesn't matter if it's slightly twisted or slightly moved to left or right or something like that. So it gives you kind of like a bit of robustness. You could also think of it as potentially giving you a little bit of scale invariance, just a little bit. Because we're not, I mean, if we're seeing a lot of vertical line or a little bit, we're going to get the same amount of activation after the max pooling. So it gives you that a little bit, but you might need larger patches to have more scale invariance, or you might need to have more layers of this happening for you to really see that happening. Okay, so that's max pooling. So what is all of this doing? Why is convolution a good idea? So I've already tried to pitch to you that convolution is giving you translation invariance, which is really important in images. Images are is a special kind of problem where there's a lot of translation invariant structure. Like if you think about your visual system, you look around, it doesn't sort of matter where in your field of view you see some things, you'll recognize them as the thing, right? However, I would argue that our visual system is much more context dependent. You know, if you see some things up in the air, or if you know you're inside a building, you'll see a picture of a tree on the wall as a poster. You won't necessarily see it as a real picture, a real tree, right? So we use a lot more context. If you train a neural network on just images, it doesn't know any context. It doesn't understand the world, right? So there are some things it's not going to do as well at. But one thing it does is it exploits, CNNs exploit structure in the problem. So this is an important thing in machine learning. You could ignore the problem and just treat it as a data set and not think about your features. CNNs don't do that. So CNNs notice this translation invariance, but also if you think about it, because we're sharing weights in a convolutional layer, we have way few parameters to learn. So we're constraining the network. If you compare it with a fully connected layer, where you can have lots of parameters, it's more flexible, but if you don't need that flexibility, you're just more likely to overfit to noise, right? If you constrain your weights to be the same as each other, or just share them, same thing, they're not different in any way, these two statements, that's a form of regularization. So we're like limiting the model class somehow. So you could view CNNs as regularizing. So that kind of lets you have more layers, because you're sort of not wasting parameters on each layer. Okay, so as promised, here's a crazy architecture, and I'm sure that some layers have been dropped, and it's a little bit hard to read from the back. I apologise, but you know, sort of reading it out loud, we're classifying documents, and structure of text is important, just like in images. So in text, there's like part of speech. So you have nouns or verbs and that kind of thing, and the locations of these low-level features affect each other. You tend to have, you know, nouns and verbs maybe near each other in some languages, in others not. Subjects of the sentence and objects and that kind of thing. And then you have phrases within sentences and et cetera, right? So there's structure to it. But some of the structure in text, like in images, it doesn't matter where in the sentence you see something. It's kind of it works in the same way. So that's why you might want to use a convolution in some of your layers. So what is the kind of stuff that this is doing? So, okay, the cat sat on the red mat. So projected sentence matrix, whatever that is, wide convolution, dynamic K-max pooling, then wide convolution. then folding, which I assume is like flattening, and then max pooling, and then we have a fully connected layer at the end for doing like multiple classes or something like that. But you can see along the way, there's some separate things here that either don't interact or do interact, and any of these things are possible. Yes, question?
How does that compare to something like bidirectional LSTM in terms of performance?
How does this compare to bidirectional LSTM in terms of performance? I have no idea. And I think the thing is, with most of these, with most answers to that question, the answer should be it depends on the data. Even if people are finding that one is better than the other at the moment, it's, people then find, oh, we were overfitting the benchmark data set that we're using forever all along. We have to start again. But I don't know in that particular case. Yeah, but good question. Yeah, maybe others will have thoughts. So feel free to discuss on LMS. Okay, so that's an example of what an architecture could look like, though. You could have you could imagine having outputs of layers come back from the top of the network down to the bottom, or from the middle down to the bottom, and you could have recurrence that way, like recurrent neural networks. You could do time series. There's a lot of flexibility in how you kind of structure these things. Cool. Autoencoders. So this is another little idea that I thought, oh, this is cool to talk about. It also connects to other things in the subject, so another reason I chose to talk about this. Okay, so we've talked about supervised learning. We use X's. We want to predict Y's. Okay, we haven't talked about unsupervised learning, but you've got X's, right? And you don't have Y's at training time. And you're looking for structure in the X's or something. You're trying to do dimensionality reduction, you're trying to cluster, you're trying to do like fit a model or something. Okay, so in the idea of autoencoding, we're going to use a tool, the neural network, that can do supervised learning. So it can output Y's, and we can measure how good the Y's are with respect to losses. So we're going to use that tool. We're going to use a supervised learner to do unsupervised learning. So we're going to try to predict the input features. So we're going to use the input features to predict the input features. And so the astute student will say, hold on, I know how to do that really well. How about we just output the input features? But the catch is, along the way, we want to drop a lot of information. So we want to compress, or we want a dimensionality reduction. We want to reconstruct the features as well as possible using, as our tool, a neural network. That's basically autoencoding. But let's talk about it a little bit more. Okay. This is pointless, right? So, no, it's not pointless. What makes this even more confusing for the first time you see it is that you might be using this when you do have labels. Okay, so you might really have labels, and it's like, why would I do this? Why would I ignore my labels? So we'll talk about how we'll use this in a minute. But even if you have labels, ignore them, right? So we're just going to look at our instances, our training instances, and we're only going to look at the input features. And we want to train a network whose output layer has the same shape as the input layer. Okay? So we're going to predict as our Y's, our X's. But the critical thing is there's going to be what's called a bottleneck layer in the middle. And maybe you get thinner and thinner as you get there or not, it doesn't really bother me, whatever. But the point is, you're going to have a very narrow layer in the middle. And so the intuition is that we are throwing information away, maybe. Or we're throwing away the information that kind of depends on the other information. Another view is we're trying to find something semantically meaningful about our data. Another view is we're trying to compress. All of the above. We're trying to do dimensionality reduction, whatever. Okay. Or we're trying to encode. So from like a coding theory, electrical engineering viewpoint, we're trying to encode our input data via some coding scheme. So given an input vector or matrix or whatever, we can output a low-dimensional code that represents the data efficiently. Okay, so how do you do this? Well, it's kind of, just in case it's not clear, you just use everything we've talked about already. So you could use L2 norm, L2 loss as your, for your training error. And you present the network with inputs. You let it make predictions on randomly initialized weights, for example. And then you see how bad you are with square loss. And then you backpropagate that error and you improve the weights until you can recover the inputs accurately. And then you've trained this thing up. Okay, so you can use it for compression and dimensionality reduction by basically, once you train this thing, you can throw out the decoder. So you can, let's call this part of it encoder and this part of it decoder. You could actually just slice off after the bottleneck layer. You could slice all of those layers off and output the values of the code and say that's dimensionality reduction, okay, or compression. If your activation functions were linear and you were using square loss, this would look a lot like principal component analysis. In fact, it would actually be mathematically the same thing. So, or if you had small randomly initialized weights and you had an activation function that was linear around the origin, like hyperbolic tangent, and you did early stopping, your activation functions would tend to be locally linear, and you would also be effectively having like sort of PCA. So this is similar to other things we're going to cover later. We're going to cover PCA after we do SVMs, because PCA is a kernel method. But it goes about it another way. And so another thing you can use this for is if you really did have true labels, what you could do is you could pre-train a network this way. So I want to have a network to predict interesting labels. I'm going to pre-train it by training up an autoencoder. And I could do this on a larger data set that doesn't have labels, for example. So I could pre-train on a larger related data set. But I'm basically sort of looking for some good features, some like semantic features or something that have something to do with my inputs. So I could train up an autoencoder and keep the encoder as like my first few layers of a network, and then add more layers on whose output try to predict some labels I've been given, some Ys. So you could do that as like a pre-processing step if you like, or transfer learning, sort of using part of the model from one data set for another. Okay, so there are lots of tools that do all of this stuff. And you'll be playing with an important tool in workshops. And all of these things are used in industry, right? And so, and some of these tools can be used for things that aren't deep learning. And really, to me, what's exciting about deep learning beyond neural networks is the engineering side, like these tools. It's not necessarily just the machine learning. It's that there's been a lot of innovation in the software. Okay, so I've talked about adding more layers. And really, I think CNNs are pretty interesting, but they're not useful for everything. Autoencoders is another cool idea out of neural networks that's fairly recent. In workshops this week, you'll be starting to play with neural networks. You will be next week as well. And so Thursday, we'll start with kernel methods, with going in depth into the SVM. Okay, see you Thursday. Thanks.